Hey there, and welcome. Today we're going to dive into one of the most important processes in all of chemistry, redox reactions. It's this non-stop dance of electrons, a constant give and take that powers pretty much everything, from the battery in your phone to your own body. So let's jump right in. So let's start with something you've probably seen 100 times, self-darkening glasses. You walk outside into bright sunlight and boom, they turn into sunglasses. Then you go back inside and they lighten up again. It almost feels like a little bit of magic, doesn't it? But of course, it's not magic, right? It's all chemistry. So what is the secret? What's going on inside that glass that allows it to react so perfectly to a little bit of sunlight? Well, the secret is something called a redox reaction. You see, trapped inside that glass are tiny little silver and copper ions, and they're basically shuffling an electron back and forth. When UV light hits the lens, an electron jumps from a copper ion over to a silver ion. That creates actual silver atoms, which clump together and darken the glass. Then, when the light goes away, the electron jumps right back, and the glass becomes clear again. It's all about that one tiny electron changing partners. So, to really understand what's happening in those glasses, and honestly a ton of other things, we've got to get to the bottom of this electron shuffle. We need to figure out what redox actually means. Now, way back in the day, chemists had a pretty simple idea. They thought it was all about oxygen. If something gained oxygen, like when magnesium burns, they called it oxidation. Makes sense? And if something lost oxygen, they called it reduction. Simple enough. But what about our glasses? There's no oxygen in that reaction at all. So, the definition had to evolve. Chemists realized that oxygen wasn't the real star of the show. It was the electron. And this right here is the modern golden rule. Oxidation is the loss of electrons. Reduction is the gain of electrons. That's the heart of it all. So how on earth do you remember that? Well, luckily for us, there's one of the most famous mnemonics in all of chemistry: oil rig. Just think of it. Oxidation is loss. Reduction is gain. Oil rig. This little phrase is your key to unlocking just about every redox problem. All right, let's break that down. Oxidation, the loss of electrons. A perfect example is a sodium atom. It's got that one lonely electron in its outer shell that it's just dying to get rid of. When it loses that electron, it becomes a positive sodium ion. It has lost an electron, so it has been oxidized. Simple. And reduction, you guessed it, is the exact opposite. It's the gain of electrons. A chlorine molecule is more than happy to snatch up a couple of electrons and become negative chloride ions. It gained electrons, so we say it has been reduced. And here's the key thing. These two processes are a team. They always happen together. You can't have one without the other. Okay, so losing and gaining electrons is pretty straightforward when it's obvious. But what about in more complex molecules, where electrons are just being shared, not completely given away? How do we keep track of the shuffle then? Well, for that, chemists came up with a really clever scorekeeping system. And that system uses something called oxidation numbers. Think of it like a pretend charge that we assign to an atom. We basically imagine that all the bonds are perfectly ionic, even when they're not. It's a neat little trick that lets us see where the electrons are hanging out and track how they move during a reaction. Now, of course, there are a few rules to this game. An element all by itself is always zero. A simple ion, its oxidation number is just its charge. Easy. And then you have some elements that are just super reliable. Group 1 metals are always +1, oxygen is pretty much always -2. Using these rules, we can figure out the score for any atom in almost any situation. And this brilliant little scorekeeping system gives us our most powerful definitions yet. Are you ready for this? Oxidation is simply an increase in the oxidation number. The score goes up. And reduction is a decrease in the oxidation number. The score goes down. This method works for every single redox reaction out there. It's fantastic. All right, theory is great, but let's put this system to the test. Let's see it in action. Here we've got some tin reacting with nitric acid. On the surface, it just looks like a chemical reaction, but if we use our oxidation numbers, we can uncover the secret story of what the electrons are really doing. Let's track those scores. The tin starts out as a pure element, so its score is 0. After the reaction, it's part of a compound, where its score is +4. It went from 0 to +4. Its number went up, so it was oxidized. Now look at the nitrogen. It starts at +5 in nitric acid, but it ends up at +4. Its number went down, so it was reduced. See? Once you know the rules, it's just simple scorekeeping. Okay, so now we know how to track the changes. Let's talk about the players that cause those changes. In any redox dance, you've got two partners, the one that's doing the oxidizing and the one that's doing the reducing. So, an oxidizing agent is the substance that causes something else to be oxidized. It's the electron thief of the reaction. But here's the twist. In order to steal electrons from something else, it has to accept them. And what do we call gaining electrons? Reduction. So the oxidizing agent gets reduced itself. And the reducing agent is, you guessed it, the exact opposite. It's the generous one. It causes reduction by donating its electrons. But by losing those electrons, what happens to the reducing agent? Well, it gets oxidized. It reduces something else by getting oxidized in the process. Let's circle back to our tin and nitric acid reaction. Who's who? Well, the tin gave away its electrons, causing the nitrogen to be reduced. So the tin is the reducing agent. The nitric acid, on the other hand, took those electrons, causing the tin to be oxidized. That makes nitric acid the oxidizing agent. It's that simple. Okay, just when you think you finally got all the rules down, chemistry loves to throw in a fascinating curveball. What if a single element could be both oxidized and reduced in the very same reaction? It sounds a little crazy, but it happens. And it has a really cool name. It's called disproportionation. This is a very special kind of redox reaction where some atoms of an element get oxidized while other atoms of the same element get reduced. It's like it's playing both roles in the electron shuffle at the exact same time. A classic example is when you bubble chlorine gas through cold sodium hydroxide. All the chlorine atoms start with an oxidation number of 0. But look at the products. Some of those chlorine atoms have been reduced, ending up with a score of -1. At the same time, other chlorine atoms have been oxidized, ending up with a score of +1. The same element, taking two completely different paths. Pretty wild, right? So, we started with a simple pair of self-darkening sunglasses, and from there we've uncovered this whole hidden world of electron shuffling, scorekeeping, and chemical agents. And the reason this all matters so much is that redox isn't just some niche topic. It's one of the fundamental processes that builds and runs our entire world. I mean, just think about it for a second. That rust on an old car, that's oxidation. The power coming out of a battery, that's just a controlled redox reaction. The very process of respiration happening in your cells right now, the thing that keeps you alive, it's just a long, complicated chain of redox reactions releasing energy. This electron shuffle isn't just something in a textbook. It's the engine of our universe. Something to think about.